NASA's Jet Propulsion Laboratory presents the Von Karman Lecture, a series of talks by scientists and engineers who are exploring our planet, our solar system, and all that lies beyond.
Good evening, everyone. How are we all tonight? Just an update, it doesn't look like, at least not yet, that we're going to have a printed brochure for the lecture schedule this year. So, I know, I'm sorry. But it is on the website, and if you give our office a call, we can put something together and try and mail you if you need it that way, okay? All right. So on December 24th, 1963, a memo from Dr. William Pickering, JPL director at the time, announced the establishment of the Deep Space Network. Prior to this date, antennas had been built at the Goldstone site in California's Mojave Desert, and overseas sites were being developed in Woomera, Australia, and Johannesburg, South Africa. However, Dr. Pickering's action combined these disparate elements to create the first integrated global communications capability to deep space. During the ensuing 50 years, the network evolved, adding new antennas, increasing the size of some existing antennas, and most recently developing a unique communication system with the widely used 34-meter beam waveguide antennas. This talk will discuss the network's evolution and the critical role it has played in space exploration. Tonight's guest is a chief scientist of the Interplanetary Network Directorate at the Jet Propulsion Laboratory. He received his PhD from Cornell University, was a U.S. National Research Council Research Associate at the U.S. Naval Research Laboratory, and was a radio astronomer on the staff of the U.S. Naval Research Laboratory before joining JPL. He has served as project scientist for the Square Kilometer Array, the deputy director of the Lunar University Network for Astrophysics Research, which is part of the NASA Lunar Science Institute, and as a project scientist for the U.S. Virtual Astronomical Observatory. He was the deputy principal investigator for the proposed Dark Ages Radio Explorer, which will be a lunar orbiter designed to make the first measurements of the effects of the first stars on their natal gases. And he's also involved in efforts to make a direct detection of gravitational waves and test one of the remaining unverified predictions of Einstein's theory of general relativity. And he still finds time to make regular observations with the world's premier ground-based radio telescopes, including the expanded Very Large Array, the Very Long Baseline Array, and the Green Bank Telescope. Ladies and gentlemen, please help me welcome tonight's guest, Dr. Joe Lazio.
Thank you. And you can hear me now? Excellent. Thank you. It's a great privilege to be able to stand here and actually describe what may very well be the most important science tool of the past 50 years. Which right this moment, those of you at least in the audience can tell, is bringing down data from spacecraft across the solar system. I've just made an extremely audacious claim, and I've sort of assumed, although Mark gave a very nice introduction to it, that you know what the Deep Space Network is. Let me back up. Let's start at the beginning of the story, 1963. Actually, my apologies. You don't know who these four lads from Liverpool are because they haven't appeared on the Ed Sullivan Show. And of course, if I was really fashionable because we don't know that smoking is hazardous to our health, I could be smoking a cigarette up here. I'm sure you've all gone and seen this very thrilling movie that came out at the end of last year, starring Peter O'Toole as the enigmatic Lawrence of Arabia. You will respect French cooking this year. It was the end of the Mercury program. Gordon Cooper flew Faith 7 multiple times around the Earth, doing actual orbits. This closed down the Mercury program, and the United States is now shifting gears. NASA is now shifting gears to the Gemini program to start doing the actual prototyping and taking those steps that will take humans to the moon. It was a year of inspirational, although at the time perhaps unappreciated talks. It was a year that had its sober moments. And if we think about communications, the state of communications at the time, there was a hotline between Moscow and Washington, but it was not a red telephone. It was this thing, more accurately described, say, as a teletype. And had my, say, grandparents attempted to call a family back in Italy, well, there was intercontinental phone service, but you shouldn't really depend upon it. And as Mark already indicated, William Pickering and others here at the lab took the steps to lay the infrastructure for what is now the Deep Space Network, starting to build the antennas and integrating them into a coherent whole. Today, the Deep Space Network is a network of 3 ground stations around the world. There's one at Goldstone, located on the Fort Irwin military base, about 3 hours up the road on I-15 from here. There's one, as Mark has already alluded, in the nation of Australia, just outside its capital of Canberra. And the 3rd ground station is now in the nation of Spain, outside its capital, Madrid. You can see that at each site, there are, anywhere from 2 to several 34-meter diameter antennas, and each site also has a 70-meter antenna. Now, just to put that into perspective, or to remind you what 70 meters means, 70 meters is almost the size of a football field. Okay, this is an antenna that's almost the size of the football field that can point to any position in the sky. And again, bringing down data from all over the solar system. These antennas are used either to command spacecraft, send commands up to, for instance, conduct some kind of measurement or repoint itself, to bring the data back down. And then this, I believe it's this one specifically out at Goldstone, the 70 meter, is used to actually transmit radar observations or transmit very intense radio waves, detect the reflections, and I'll return to that point. It is the ultimate long-distance carrier, and in fact, it gets more ultimate every day. This number is actually out of date now. Perhaps you heard last year that the Voyager spacecraft, so Voyager 1 actually, this is the demonstration model, if you will, but the real model is actually outside the solar system now. We can say, in some sense, we are an interstellar spacefaring civilization. We have sent something outside the solar system, and the only way we can communicate with it is in part due to the foresight of William Pickering and the other people here at the lab that started establishing the Deep Space Network and constructing these large antennas. What's the big deal, though, about these big antennas? Because if any of you have a satellite dish, satellite TV at home, you're actually receiving data down from a spacecraft or a satellite. Now, those spacecraft or those satellites sit typically out at geosynchronous orbits. It's a special orbit that has a period of 24 hours, which means it sort of more or less hangs over the continental US effectively. And again, you've got a dish that you can more or less hold in your hand. What's the big deal? Well, the big deal is a very basic law of physics that as you move, say you take any source of essentially light or radio waves and move it farther away, it gets dimmer. And you've all experienced this, of course. There's a very secure law that, for instance, if you move something twice as far away, it gets 4 times dimmer. You go 10 times farther away, say you go from the distance of geosynchronous spacecraft to the orbit of the moon, something is now 100 times fainter. And if you want to start talking about exploring the solar system, say going out to Jupiter, you're talking about 500 million times fainter. So to pick up those kind of signals, you need very large antennas. Okay, 50 years of science. How do we understand that? Just if you think in terms of technology and engineering, for instance. When my grandmother was born, of course, heavier than air flight was something just better than a curiosity, and she watched humans land on the moon. How do we capture this? Well, interestingly, there's a group called the Council for the Advancement of Science Writing, so completely independent of JPL. They came up with their top 50 list starting in 1957. Now, to astronomical accuracy, 1957 and 1963 are pretty close. So let's use this Council of Advancement of Science Writing, their top 50, as an illustration of the kind of progress, scientific progress, that happened in the last half of the 20th century. Of those 50, what I'm going to attempt to convince you is that the DSN was intimately involved in some aspect of 22 of those. And I think that is a pretty impressive record. Start at the top. Number 1, satellites. This was, of course, the raison d'etre for the Deep Space Network. Of course, the real motivation for this was Sputnik. And one of the reasons that Sputnik was so scary was from the standpoint anybody could pick that signal up with a ham radio equipment. It did not require a lot to get the beep beeps from Sputnik, and it really demonstrated the ability to put something up in space. But if you want to start thinking about going beyond so-called low Earth orbit, perhaps 300, 400 kilometers up, and you really want to start thinking about going to the moon or going to other planets, you need some kind of substantial infrastructure on the ground. So Sputnik helped motivate the need, but then once you started building it, you can start thinking about going well beyond simply just above the Earth. There was some non-DSN science occurring during the last 50 years of the 20th century. Remember this one, I'll come back to it. Plate tectonics is a topic that those of us in Southern California might have a special interest in. It may seem surprising, but when the notion of plate tectonics was first introduced, it was extremely controversial. The notion that continents can move, these big things can move. Now, even a child can look at South America and Africa and sort of note that they fit together, but how do you actually show that they move? One way that you show that they move is suppose you have very sensitive antennas that are looking at a distant object, and there are ways of processing the data that will actually allow you to determine very precisely the distance between the antennas, down to centimeter precision, which means you can then watch, do the antennas move over time? And sure enough, if you look at, for instance, an antenna in Europe and an antenna in North America, they separate. The continents really are moving apart. Today, these kind of measurements are done with GPS, but when the field was very new, when we didn't have GPS, doing things like measuring very precisely distances between DSN antennas was one of the key pieces of evidence that really convinced people, yeah, the continents are moving around. The modern environmental movement owes much to this book by Rachel Carson, of course, describing the influence of pesticides. But arguably, one of the other significant influences was a picture like this, or this picture, transmitted back by Apollo astronauts through the Deep Space Network, showing our home planet, that big blue marble, sitting there in the inky darkness of space. That is home. That's the only place in the universe we know that supports life. And if that doesn't cause you to sort of appreciate what this planet is, and of course, in some sense, both our uniqueness and the need to protect this home planet, the only place we know that supports life in the universe, what will? Quasars, one could give an entire von Karman lecture on quasars. Today we understand that these are likely to be supermassive black holes at the centers of particular galaxies. They were actually discovered in 1963 and extremely enigmatic at the time. And the name itself actually comes from quasi-stellar radio source. Now, the importance of this is that if you think back, how did we used to navigate? Well, you give me a tall ship and stars to steer her by. Okay, if you're going to send spacecraft through the solar system, how are you going to navigate them? Particularly if you have big antennas on the ground and you're communicating with radio waves. Now you have essentially point-like radio sources in the sky that you can use for navigation. And one of the important contributions of the DSN was, if we're going to do this, we now need to find out where they are. We need to determine the positions very accurately. And that is, in fact, one of the clues that helps us understand what these objects are. So the DSN played a critical role in helping expand the catalogs of quasars and contributing to us understanding so that today I can stand here and tell you something like, well, they're likely to be the active cores or active supermassive black holes in the cores of galaxies. Mid-60s, we're also finding out that protons and neutrons, things that we thought were fundamental particles, may in fact themselves have constituent structure. The cosmic microwave background, you will hear me refer to this multiple times. It's kind of the gift that keeps on giving, if you will. Discovered completely accidentally and by some engineers at Bell Lab. But all of the initial work on the cosmic microwave background was done from the ground. The key measurements, though, were done from space and could be done from space by, for instance, the WMAP spacecraft well away from the contaminating effects of the Earth because we had these big antennas on the ground. They could transmit down the data. And in fact, this picture here, just briefly for reference, this is essentially a picture of the sky. Think of this as being north or up, and that's south or down, and then it wraps around you. And the crucial thing about this, one of the reasons that this image, which is actually an image, if you will, of the very distant universe, the fading glow from the very distant universe, where you see these are spots where the sky is essentially a little bit warmer, a little bit colder. And we think the warm spots are probably the seeds of what grow into today we recognize as large clusters of galaxies. The other very interesting thing about the CMB is not only has the DSN been crucial in helping study it, the amount of power that comes from the CMB is small, But the DSN itself is so sensitive that when you start trying to make spacecraft links or communicate with spacecraft across the solar system, you have to take into account the amount of power that the CMB provides to the DSN. There were some important medical advances, of course, and by the late 60s, we're actually landing humans on the moon. If any of you were alive at the time, those pictures of Neil Armstrong bounding down the ladder, and then subsequent pictures of astronauts driving around the surface of the moon in rovers. All of those kind of images relayed back through the DSN. And again, through the foresight of the people working here, at least a decade earlier, we had the infrastructure that we could do those kind of observations and that kind of experiment. The internet, you might think there's not a lot of commonality between the DSN and the internet. The internet itself, actually the ARPANET, which was the precursor to today's internet, was set up as a robust communication system. In other words, when you send email from your home computer to your friends, even if there's a computer down along the way, the internet or the underlying protocols are smart enough to figure out there are ways to transmit the message. Well, think about the DSN. We have 3 ground stations. We're redundant. So a spacecraft, we may have to wait a little while if one of the ground stations is out for one reason or another, but we have that kind of redundancy. We can always get the message through. And in fact, we're looking at ways, and I'll get back to this, of essentially making an interplanetary internet, expanding on that idea. We're learning something about cancer. And you've noticed I've skipped over a lot of the medical stuff because in general, looking out into space may not immediately lead to medical advances. But here's an interesting aspect in which it did. Early 70s, there's this thing called computer tomography invented, which is really revolutionary. Instead of going from an X-ray of an arm, a static 2-dimensional picture of somebody's arm, we now have 3-dimensional images of the human body. And of course, this has now been superseded by MRI and PET and things like that. But you can actually you can make 3-dimensional images inside the human body, and you can actually watch things change over time. The interesting aspect of it is that the underlying mathematics that allow you to make these kind of images, that is built upon a foundation that is the same kind of processing that we use in the DSN and in other radio telescopes to process the data coming down. So it's a remarkable, again, the people here at the lab, when they set up the DSN, they were not trying to enable better medical scanners. But sure enough, something like 15 years later, that's an outcome of that kind of investment. And it's also indicative, the kind of timescales that we're talking about. You start the DSN actually before 1963, as Mark indicated. 1963 is in some sense the birthing of it. But it takes potentially a decade or more for that kind of initial investment to pay off into, here's an initial discovery in medical imaging, and then it comes into real use really about a decade later. Early to mid-70s, we're also learning some more about biology, about our own ancestry. We're learning that we can have a global impact on our planet. And by the mid-70s, we're not only taking pictures, we're not only sending spacecraft past other planets, we're able to navigate to them, we're now actually landing on them. So this is a picture of the Viking lander, one of the Viking landers is going in to land on the surface of Mars. And you might, as I've already guessed the punchline here, of course we can't think about navigating landers to another planet, landing and getting pictures back without having the infrastructure of the DSN. And in fact, these kind of pictures that come back today of things from like the Mars Opportunity and Curiosity rovers continue to come back through the DSN. We give ourselves an honorable mention in the case of deep sea life. Of course, that means looking down or going down to the depths of the ocean, which is the opposite direction from which the DSN looks. And it actually, again, it was a remarkable discovery, if you remember this. This is a so-called black smoker, where there's super heated water laden with chemicals that's spewing out. And it's not immediately obvious in this picture, but there's actually life around this thing at the bottom of the ocean. Now, the honorable mention aspect is that when the folks who were trying to do the underwater exploration or the underwater robotic vehicles were trying to figure out how to communicate with their robotic vehicle at the bottom of the ocean, they came knocking at the DSN doors because communicating with spacecraft on the other side of the solar system has many commonalities. The other, of course, important thing about this kind of discovery that may tie back to the DSN in the future is if we can have life underneath the Earth's oceans that does not depend upon sunlight, maybe there can also be life, say, in other oceans. We now know that there are other oceans in the solar system, underneath ice shelves. And of course, if you're going to do that, how are you going to get the spacecraft there, and how are you going to get the data back? We've already made mention of the Voyager spacecraft. In fact, and Mark alluded to this, there was a nice alignment of the planets in some sense in the early to mid 70s. You could send a spacecraft, you could send a Voyager spacecraft to Jupiter, and then it would get accelerated in a way that it could go to Saturn. And then in particular, one of the two Voyager spacecraft, Voyager 2, was targeted past Saturn in a way that it could keep going to Uranus and Neptune. And as I've already indicated, Voyager 1 has in fact now become an interstellar spacecraft. An interesting aspect of this is, in order to keep up with the Voyager spacecraft as they're moving farther away, the DSN antennas were actually expanded. The original dimension of the largest antennas was 64 meters, but they had to make them larger because as this spacecraft keeps moving farther and farther away, the signal keeps getting weaker and weaker. There's some more biology, data encryption, I won't go into that, but there are some potential future linkages to the DSN. Killer asteroids. Today, killer asteroids is perhaps, again, not a particularly, you can see comics about it, and I think comedians make jokes about it. But again, when the notion was first proposed in the early 80s by Walter and Louise Alvarez, this was incredibly controversial. The notion that actually something would come in from outer space and globally affect the climate. One of the key aspects, or among the various aspects that have contributed to actually this idea being taken very seriously, is both the sending of spacecraft to things like asteroids and comets, and I'll come back to that point. It's also, you remember I made comments at the beginning about how the DSN actually transmit radio waves in a radar mode and gets reflections. These are reflections from an asteroid. So it's turning from points of light into actual bodies. The other very important aspect, and why it's important from a collision or a planetary protection aspect, is that if you transmit a signal from a DSN antenna, you can time how long it takes to go to the asteroid and back. You get the distance very precisely. You can actually there are ways to watch how the signal is reflected and tell how fast the asteroid is moving. You nail down its orbit, so you tell not only where is it today and how fast it is moving, I can tell you 100 years from now, 1,000 years from now, where that asteroid is going to be, which is, of course, very important. Cosmic inflation, this goes back now to the cosmic microwave background. If you look very carefully at the data and you understand the general theory of relativity, there's actually some subtle issues with the cosmic microwave background. And Alan Guth and independently some Russian investigators essentially simultaneously proposed this notion that it may be the result, all of essentially the observable universe that we see today may be the result of a quantum mechanical fluctuation very early in time, and it expanded. But in any event, much of that comes from looking at the cosmic microwave background. There have also been tests of this kind of idea of looking for deviations or understanding general theory of relativity by watching how spacecraft signals propagate across the solar system, in effect turning the DSN and a spacecraft into a solar system scale instrument. We're accelerating here now. There's lots more progress, as you can see, everything from, again, biology to novel ideas in particle physics, nanoengineering, as it were. Once again, going back to comets, with our international partners, there was an armada of spacecraft that went after Halley's Comet. Of course, all of the data came down through the DSN. The one that got the closest was the European space agencies. And again, I think this is an important aspect of the international aspect of science. We work cooperatively with our international partners, whether it be ESA or the Japanese in JAXA. We've worked with Roscosmos, the Russians. So we work internationally. The Giotto spacecraft was the one that got the closest and got these pictures of the nucleus, the first pictures of the nucleus of the Halley's Comet. Well, as it was en route to the comet, it actually had an onboard anomaly or glitch, and it pointed its antenna away from Earth. Okay, that's a problem if you want to send it commands or you want to get the data back. But because of both the sensitivity of the DSN, the problem could be diagnosed, and then because of the power that could be transmitted out of these big antennas, it could effectively ping the spacecraft and get it to pay attention and reorient itself. One of the reasons that we often say that spacecraft, going into deep space really is rocket science is because once you launch that thing, you can't go out there and fix it. But there are some important exceptions in which you can imagine doing something like a million-mile screwdriver. Some interesting material science in terms of high-temperature superconductivities. A cosmic crash. This was, in fact, again, one of those examples that demonstrates very vividly that there are things in the solar system that crash into planets. This is comet Shoemaker-Levy 9. This picture was taken from, I actually don't remember if it was a ground-based or space-based telescope, but this is after it's passed too close to Jupiter, and Jupiter's immense gravitational, or strictly its tidal field, has ripped the comet apart. You now see it on a string, the string of pearls, if you will. It's also on a death course to Jupiter. But it has the audacity or the bad taste to have an orbit that collides with Jupiter when that part of Jupiter is facing away from the Earth. All of our ground-based telescopes can't see it. Fortunately, we have the Galileo spacecraft, which is actually a replica of it, is in the museum on the other side of the wall there. The Galileo spacecraft is orbiting nicely, orbiting Jupiter, and can actually see the backside. So the only way we get to witness this collision is because we can communicate with, we can get the data down from Galileo, and in fact, that's another example of this million-mile screwdriver issue. The Galileo spacecraft had a problem with its so-called high-gain antenna, which was going to bring down most of the data. So the entire mission would have been lost were it not for the ingenuity of the engineers who understood the spacecraft and having these really big antennas on the ground so that they could still get the signal back, even though it was much weaker than they had originally anticipated. There's some interesting mathematics during the mid-90s. I won't talk about quantum computing, but maybe I should be. It's an interesting aspect maybe in the future of using quantum mechanics to do communication. By the mid-90s, we're finding planets around other stars. In 1995, the first planet outside the solar system is found in 92, but it's around a very weird kind of star. In 95, we finally find planets around a sun-like star. And the initial progress is entirely by ground-based telescopes. But today, we know of something like 3,500 planets, which in and of itself should sound like an astonishing number. The vast majority of those, something like 2,500, are the result of the Kepler spacecraft, the Kepler mission. And in order to make these kind of measurements, Kepler was put out in deep space, and it brought back those signals by the DSN. Kepler has, in fact, suffered essentially a so-called reaction wheel failure. It can no longer do these prime kind of measurements, but they're trying to essentially reboot the spacecraft or restart the science mission doing something analogous but complementary, if you will. We now talk about the diversity of planetary systems, too. We used to think, oh, well, most planetary systems are probably like ours, and we now know that there's an incredible diversity of the number of planets in a solar system, where they show up. We know of planets that are unlike anything in our own solar system. And again, much of that comes in the past, actually in the past sort of 5 years from the Kepler mission. Mid-90s, we're starting to clone mammals. By 97, we're not only landing landers on another planet, because think about it, a lander is a really impressive achievement, right? You're going down and you actually get the thing to land and not crash. But the problem with a lander, or one of the problems with a lander is, suppose that thing you really want to measure, or the thing you really want to see is a kilometer, or 100 meters, or even 10 meters over there. You can't go there. With a rover, you can. And in fact, there are people just up the hill, or all the commands to tell these rovers where to go next funnel through a building just up the hill, then out to the DSN and out. So they don't quite joystick it, but essentially, these rovers are being driven from around here, sending the commands up through the DSN, and then relaying the data back through the DSN. Dark energy, perhaps some of you have heard of this. The initial observations were of a particular kind of exploding star, and they lead to the notion that the universe is not only expanding, which has been known for something like a century or 90 years, but in fact, the acceleration is accelerating. Now, the first observations, there are some subtle issues you could get yourself fooled, but again, the CMB With deep space spacecraft, you conduct these very sensitive measurements of the CMB, and it leads to an entirely different reasoning chain, entirely different analysis chain, and you end up with, there's one kind of measurement that leads to this weird acceleration, and there's another completely separate, and now you have to take it really seriously. The other thing, of course, I should point out is we give it this lofty name to disguise the fact that we have really no idea of what it is. But the DSN will support, and again, in terms of international cooperation, the European Space Agency is putting up the Euclid mission with a prime goal of trying to understand better what this dark energy stuff is. More human biology and getting into actually big data of understanding ourselves. More CMB stuff, actually. Look at that. When I was a graduate student, we knew the age of the universe was somewhere between 10 and 20 billion years old. And it's now written with 3 significant digits. And that's really accurate. So all of that kind of data come down from precise analyses of the CMB from these deep space spacecraft. We're actually, We were starting to really understand cancer in 1970. 30 years later, we're starting to talk about targeted therapy. Titan. For those of you in the audience, this is, I guess, a replica of the Cassini spacecraft. That gold disc there is the replica of the Huygens probe. Now you're actually starting to put a lander, or at least a near lander, into a distant moon of a deep outer solar system giant. These are the pictures that came back, and I suspect you know by now the punchline. They came back through the DSN. But there's an important aspect. This mission might have failed, or at least the Huygens part of it might have failed, because there's a problem that wasn't recognized until after launch. There are a couple of very key ESA engineers. They came here to California, did some testing out at Goldstone, and verified that there may very well be a problem, worked with the DSN engineers to figure out a workaround, a fix, and uploaded those commands through the Canberra station. So again, an example of international cooperation, and the only reason we can see these pictures of this satellite are because of that kind of international cooperation and because we have the DSN. The other thing that I neglected to mention, of course, why is Titan, Saturn's moon, so interesting? It's interesting because it's quite well, first off, here's an actual example. It's perhaps the only, I think it's the only place in the solar system. You actually have an atmosphere, you have solid land, and it's perhaps not immediately visible in these pictures, but there's a liquid. It's not water, but there's a liquid on the surface of this. And in fact, early DSN radar gave hints that there were these anomalous reflections from Titan suggesting that there might be liquid on its surface. And this might very well be a deep frozen relic of the early solar system, and perhaps similar to what the early Earth looked like. Some of you may remember that in about 2005, 2006, the International Astronomical Union actually came up with a definition for a planet at that time. And Pluto was reclassified as a dwarf planet. There were multiple reasons for that. One was, for instance, the discovery of extrasolar planets and the incredible recognition of the diversity. One of the other, it's not well appreciated, but there was actually, in some sense, a debate or a very vigorous discussion at the IAU General Assembly where this took place, where this vote took place. And one of the key factors was the orbits. And it had always been, Pluto's orbit had always been a bit weird. And of course, how do we know the orbits of the solar system planets, and how do we know them so well? One of the reasons is we have to navigate spacecraft through the solar system. So if you're really going to send a spacecraft past a planet or land on it, you have to know those orbits very well. So some of the crucial evidence that went into understanding that Pluto really was a different kind of object and not a planet came from the kind of navigation and understanding planetary orbits. There's real dinosaur tissue now, and maybe we're getting to the state of invisibility shields. Going back to landers, we're actually tasting water now, showing that there is at least frozen water. In this case, we knew where to set the lander on Mars, but we could relay those data back, and you actually start to see that there might be, in some sense, at least in the past, there was running water on Mars. We also know that there's water on the moon. The L-Cross spacecraft was designed to collide with the moon, and collide with part of the southern pole of the moon, where it was thought that there was water. And you might say, well, why are you going to crash a spacecraft into the moon to see if there's water? It's a pretty crazy idea unless you already have some hint that it's there. And in fact, the DSN was used to illuminate the moon with radar, or shine radar on it. And one of the things water reflects, or ice, reflects differently than rock. And so there are these parts of the moon that were reflecting differently than the rest. And in fact, it's not only the case on Moon, but we now have pretty good evidence that Mercury as well. There are places on both Moon and the Mercury that were hinted at by the radar and could motivate the idea of actually intentionally crashing a spacecraft into the Moon to actually find that. Okay, 50 years in less than 50 minutes. Let's spend a few moments looking forward. I think it was Yogi Berra who said that prediction is difficult, particularly when it's about the future. Let me try nonetheless. And let me start with some of the things that we're doing today. It's perhaps not a surprise that when you send a spacecraft to another planet, if it goes behind, if this is a spacecraft and it goes behind another planet, you can no longer see the signal from it. So if you're attempting to communicate with it, you lose contact while it's behind the planet. I fear it's not showing up too well here, but if you imagine, suppose the planet has an atmosphere. Well, as the signal passes through the atmosphere, it's going to pass through the atmosphere before the spacecraft goes behind the planet. And in passing through the atmosphere, the signal is actually affected. Now, you could say, oh, mon Dieu, this is tragedy, right? Here I am, I'm attempting to either send commands or get data back from the spacecraft, and the signal is being affected by the passage through the planet's atmosphere. Or you can take the approach, hey, maybe I can use those changes in the spacecraft signal to understand the planet's atmosphere without actually dipping into it or sending anything into it. Just by looking as I go behind the planet, I can start to understand the planet's atmosphere. Further, depending upon how the spacecraft, or as the spacecraft moves behind the planet, or as it moves around the planet, how it moves is affected by the planet's gravity, which in turn depends upon how mass is distributed inside the planet. So you can actually, in some sense, start to get a sense of how is mass, what is the interior structure of a planet. And effectively, what I'm hinting at, I've already in fact said the punchline on this one, we're turning the combination of the spacecraft and the DSN into one giant science instrument, in some cases solar system spanning. Perhaps the epitome of this in a planetary science case was GRAIL, which was a lunar mission last year, modeled on actually GRACE, which is a pair of spacecraft orbiting the Earth right now. The idea here is you have two spacecraft. Let me just use a simple example. Suppose this is the moon. This is a mountain on the moon. You have two spacecraft. I think it was a Montana classroom. They're named Ebb and Flow. The moon, or this mountain, is slightly more massive than the surrounding area. So that means there's a little bit more gravity. As these spacecraft come along, this spacecraft is going to feel that extra gravity a little bit sooner, so it's going to accelerate toward. The separation between the spacecraft is going to increase. And then this one is going to accelerate, catch up. And then as they go past, this one will slow down a little bit. They'll catch up a little bit more. And then they'll return to their normal configuration as they've gone past the mountain. So this technique, it looks very much like what I just described is in fact very much like instead of one spacecraft going behind a planet, now we're using two in tandem. And in fact, that's what this picture is supposed to represent. There the spacecraft are communicating both with the Earth and between themselves using these kind of link techniques to measure very precisely the distances. And the result is this is a mass map of the upper part of the moon. Here is effectively the equator. And this is sort of this is the near side, this is the far side. And what you can tell is there's an immense amount of structure. Some of that is perhaps not surprising. I mean, if you go out and look at the moon tonight, you'll see these mare, these very dark areas. But you can tell that there are actually differences around the moon in the amount of mass that's scattered on. Some of that might be the result of previous giant impacts. But this is the kind of thing where you not only see the surface, but you get to start to probe deep within the planet or deep within the object. Another very recent example, the paper was actually, the description of this was published only a couple months ago. Phobos is one of the two moons of Mars. It's been known for at least a century, maybe a couple of centuries. It's a very weird moon. For starters, it orbits around Mars essentially opposite the normal direction, if you will. It's also been known for, again, at least 100 years, maybe a couple hundred years, that it's not massive enough in some sense, or it's too rarefied, and it's not dense enough. When I was a boy, the prevailing model, or the explanation, was that Phobos was a captured asteroid. And part of the reason that it was so weird, or it didn't look like it wasn't similar to Mars, was that in fact it came from a more distant part of the solar system, perhaps farther out where it's more ice. And actually, this is also consistent. If you think that Mars used to be warmer and wetter, maybe it had a larger atmosphere. So this asteroid could have gone past Mars. If Mars had a larger asteroid, it would have essentially been aerobraked. It would have been captured into an orbit. It actually, the story hangs together. This ESA Mars Express, a team here at JPL collaborating with ESA collaborators or European collaborators, the Mars Express spacecraft, its orbit was set up to go past Phobos. Now, if you imagine, suppose you, in your mind, remove Phobos from this picture. Here's the orbit of Mars Express. Here's the, say, notional or nominal orbit of Mars Express. But now if you put Phobos in, that's a little additional mass. That's gravity, which means the actual orbit of Mars Express now does something like this. So by determining the tug on the spacecraft, which we can now do because we're making very precise measurements of the signal, you can actually determine what the mass is very accurately. And again, by sort of the same techniques, you can start to probe the interior of Phobos. And the very weird thing that results is that somehow Phobos has to have lots of gaps. And I fear this is not really going to show up. I attempted to make this morning. And of course, it's leaking. And I bet those of you only in the front can see. But as best I can understand it, Phobos is something like a bunch of rocks, probably with some ice holding them together. And it's partly very weird. It also implies, if you think about our own moon is a solid, it's one essentially solid object. It's not a bunch of boulders that are somehow held together by ice or somehow glued together, if you will. And the model that this team is now suggesting is that Phobos reaccreted in place. So somehow there's a debris of stuff around Mars, and that debris led to it condensed into little boulders, and then somehow those boulders were able to stick together. So rather than being a captured asteroid, it's actually something that was managed to stick itself together in orbit about Mars. And it's amazing. I mean, this is one of the neat things about science, right? We actually learn new stuff about our universe, about our solar system. And I guess my punchline, or the soundbite for this is, when I was a boy, Phobos was a captured asteroid, and Pluto was a planet. Neither of those are true. I commented about radar. This is sending. Now, most of the time, of course, what is used is you transmit signals. You don't have to transmit too much. But sometimes you put a lot of power into the antennas, into specifically the Goldstone 70-meter antenna, and transmit it at an asteroid. You see here this object, 1998 QE2. And those of you who have been watching the movie have already noticed there's something particularly bizarre about this asteroid, this little blip here, which stands out immediately. It stood out in the first reflections coming back. That's a moon. This asteroid actually has something orbiting, a natural satellite orbiting it. And this, the first asteroid moon, I think, was found by a spacecraft going past an asteroid. But subsequent to that, it's now been clear from radar observations that asteroids are a varied lot. Many of them do have moons. This is, in fact, the kind of data that one gets back. You can not only make these images in these movies, but you can actually 3D print replicas of asteroids. So this is Galivka, if I'm pronouncing that correctly. And you may not be able to see, but it's a very weirdly shaped object. And that is, in fact, it almost is the norm among asteroids, that they have these very bizarre geometries. This object, 2012 DA14, would have actually it got a bit of press last year. Here's a capture from the NBC News, and down in the actual text, it talks about how the radar return from the Goldstone radar was used to study it. If you look, these are sequences of images of the radar returns, and you don't even need any training to look at that and say, look, there's clearly something changing, right? The asteroid is rotating. You can determine how the asteroid is rotating. This thing would have gotten even more press than it did because it came within the geosynchronous belt. So you remember I described those geosynchronous spacecraft that, for instance, are used for satellite TV or other communications, they're at about 40,000 kilometers away, or essentially think of 40,000 kilometer altitude. This thing came within that. And the only reason this thing didn't get more press is because on the same day, but in a completely different orbit, a very small asteroid came in over Russia. If I've said it correctly, it's Chelyabinsk. Came in, you may have seen the pictures of the movies, exploded, and then actually remnants of it hit the ground. This is also, I mean, this helps illustrate why we need to understand these very small objects, because even small objects, say something that fits inside this room, can still do damage if it comes down on Earth. The other sort of sobering thought to think about, this asteroid exploded over the skies of Russia in 2013. Imagine what the world would be like today if that had happened in 1963. Okay, next 50 years. Now let me actually look forward. Very quickly, half of this is going to be technology, and I'll close with a bit of science. I showed this slide earlier. Remember these lasers? Of course, I'm using one right now. Again, just to emphasize, 1960, lasers are more or less invented or discovered, whichever verb you want to use. How long did it take before you started seeing these in commercial use, say in scanners in your grocery store? It took something like 35 years, right? Between the time that you actually understand the basic physics to the time that you can actually apply it commercially or make our lives better can be decades. These also have a potential impact for the future for the deep space network, in that although we use radio waves today, and those of you in the audience here, you can see these massive, essentially very large, massive radio antennas that we use to communicate with our deep space spacecraft, you could imagine putting a laser beam on these spacecraft and using the lasers to communicate with ground terminals. Now, it's sort of like, imagine, if you will, fiber optics without the fiber. And you might say, what's so impressive, or why do you want to do that? Let me just illustrate one example. Take the Juno spacecraft. It is en route to Jupiter. It will begin orbiting Jupiter maybe just about July 4th in what, a year, 2.5 years. Actually, one of the prime science aspects of the Juno mission is to dip close to Jupiter, and by monitoring the signal, we will be probing the interior of Jupiter. But you see this thing here, this is the antenna, and it's similar to the spacecraft replica in this room. That antenna is then, to communicate with Earth, is pointed toward the Earth. But a very basic aspect of physics, and I'll gloss over the details, a very basic aspect of physics is from the time that signal is transmitted to the time it reaches the beam, if you will, the beam of radio waves, by the time it reaches the Earth, it will expand. And it will expand to something like 200 Earth diameters. So the amount of power that is being transmitted is being spread over this incredible area, and we're only picking up a very small portion of it. And the amount of power that we receive directly influences how much data we can get down. And the Juno mission is scoped at minimum. They have to, or the system and in communication with the Deep Space Network, or actually, it's more like the Deep Space Network must be sure to provide at least 0.018 megabits per second. Now, to put that in some kind of context, my digital camera at home, a typical image or a typical picture that takes off a digital camera might be something like 10 megabits. So it might take something like 100 seconds to transmit an image. Now let's consider doing this at optical. First, the spacecraft itself looks very different because no longer do we have this high gain antenna on. We've got some kind of optical terminal, which in fact might only be sort of this size. The beam still spreads out. The fact that the distances are so small that you can't really tell the laser beam on this laser pointer is doing it. But over interplanetary spacecraft, interplanetary distances, it does. What you can see, however, is that the beam is much more narrow, which means the power is being concentrated in a much smaller area. We can pick it up, and we can transmit much higher data rates. If you can't see it, the expectation, if you just do some simple scalings, you could potentially transmit something like at least 2.5 megabits per second. So now your images come down in a few seconds. However, and this is one of the issues associated with actually making this operational, if you stare at this for a minute, you see a technical challenge inherent in doing this laser communication. Suppose, actually, you can see, I can't quite hold the laser pointer steady. So what happens if the spacecraft is wobbling just a little bit? It doesn't take too much for the beam to shift off the Earth, and we miss the signal completely. So one of the technical challenges in actually making this operational is the entire pointing and tracking, making sure that the spacecraft always remained accurately pointed at the Earth. I referred to this earlier, or I hinted at this earlier. Actually, if you look at the kind of communication, say, to the Hubble Space Telescope or the International Space Station, they very often don't go directly to the ground, but they'll go through a network, a space network of relay spacecraft, which are supposed to be represented by these orange lines, which can communicate from themselves, and then they will be transmitting the data down to the ground. In some sense, this is internet-like, because if a signal doesn't go through with one spacecraft, you have another shot to get it. We have a crude example of that at Mars. So in fact, very often the rovers do not communicate directly with the Deep Space Network, but they send their signals or they send their data up to one of the orbiters, which collect the data, and then when it's in view of the Deep Space Network, it relays it back to the DSN. Now you could start to say, why don't we have something like an internet at Mars, in which we have a network of relay or communication satellites so that no rover is ever out of communication. We have redundancy, we can tolerate any kind of disruptions. And in fact, that's kind of where people are thinking. And in fact, why not be ambitious? Let's spread that throughout the solar system. If you're thinking about sending humans back into space and back into deep space, you want reliable, robust communications that aren't susceptible to disruptions, which is very much internet-like. Let me just close with a couple notes about science. Everything I've been talking about, the radio waves that are used to communicate, this laser pointer, all of those are electromagnetic waves. Another way of thinking about it is, here's the rainbow that our eyes see. I suspect none of you will be surprised to hear that there are colors of light that our eyes cannot see. If you've ever received a sunburn, you've had a direct experience with ultraviolet light. If you've ever had an X-ray, you've had a direct experience with X-ray light. Radio is simply a color of light more red than red. It's beyond, in fact, there's infrared, which is more red than red, and then there's radio, which is beyond infrared. That's the kind of signals that we use to communicate with. Completely analogous, there's a prediction that there should be gravitational waves washing throughout the universe. And you probably can't read this slide. The details, I'll gloss over the technical details in the interest of time, but essentially, just like stars produce light and there are various sources that are producing radio waves in the universe, there's a prediction that there should be various things producing gravitational waves. Now, why do you care? There are several reasons. One is, this is an untested prediction of Einstein's theory of general relativity. Some of the precursor work has already yielded a Nobel Prize in physics. So it's very high-profile science. For those who know what it means, the US astronomy community has actually identified this as a potential discovery area in a decadal survey. And in order to generate these kind of things, you need very extreme environments. The only reason we actually stick to the Earth, or stick to our home planet, is because the Earth is so massive that it produces strong enough gravity to hold us in. This picture, if you've been watching the movie, in order to generate gravitational waves, you need extreme environments such as in-spiraling and colliding black holes, moving at very high velocities, and then they produce these gravitational waves. So it's another way, actually, of probing the universe, and it may give us a new view of the universe. There are different ways of looking at how you would detect gravitational waves, but essentially all of them depend upon a scheme like this. The idea behind gravitational waves is, suppose there's a gravitational wave washing over us right now. What it does is it very subtly changes the distance between two objects. And you can see in this picture, here you have two arms, and the distance as the gravitational wave washes over them, if you can monitor that distance very precisely, you can tell that there's a gravitational wave, and particularly, not only that they change, but they change in a regular fashion. There are ground-based efforts to do this. There was once upon a time, and I think it will still come back, a notion of a space-based mission that would communicate via laser beams to monitor the distances. These Cassini spacecraft, or the Cassini and DSN spacecraft, Cassini spacecraft and the DSN, have actually been turned into a solar system scale gravitational wave detector, because again, if you can monitor the distance between a spacecraft and the Earth very precisely, you can then detect are there gravitational waves, or at least constrain are there gravitational waves washing over the solar system. In fact, this notion was first suggested by a couple of researchers here at JPL. And there's a long history of doing this, first with Pioneer, then with Viking and Cassini. And it's actually a case of continuing to push down on the theory. To date, there's been no detection, although right now the observations are enough above the predictions that it's okay. Looking into the future, there's a class of stars known as pulsars, and I'll gloss over the technical details, but effectively think of them as cosmic clocks. So they allow you to detect very subtle deviations in the distance between, say, a pulsar and you. And this animation is, in fact, showing we have very good, wow, it's pretty secure. Galaxies collide. We have good evidence to suggest that in the heart of most galaxies are supermassive black holes. So that should imply that there are galaxies where there are supermassive black holes spiraling around, generating gravitational waves, which are these supposed to be represented by these green things coming toward our Milky Way galaxy. And if you can conduct very sensitive timing observations of these pulsars, you can essentially monitor the distance between a pulsar and us. And in fact, in the best case, we monitor the distance, or a team of astronomers in North America monitors the distance between a pulsar to something approaching the scale of a football field, even though it's hundreds or thousands of light years away. This technique was actually pioneered at JPL using DSN antennas. Somewhat unfortunately, the guys were ahead of their time. There are different kinds of pulsars, and at the time they didn't know of any of the right kind of pulsars to observe. We've now found enough of those kind of pulsars, and we're in the process of making sure that the DSN is back in this game and actually helping to test Einstein's theory of relativity. Looking both into the science and into the technology, these are CubeSats that were released, I believe, from the International Space Station. CubeSats, for those who don't know, the basic CubeSat is 10 centimeters by 10 centimeters by 10 centimeters, so it's literally something you can hold. And they come and you can stack them. Think of something about the size, say, of a shoebox. And JPL will be flying two CubeSats in a mission called INSPIRE. In fact, one of the things it's supposed to do is demonstrate communication between these two. Now, instead of, the attractive aspect of this is, remember I said there was a Huygens probe. Galileo also had a probe that went into Jupiter. If we can have deep space CubeSats, or maybe small sats, is there something you can hold in your hand? Let's now start thinking about not onesies in orbit around a planet, but let's start sending fleets of spacecraft to planets, or sending probes, multiple probes into planetary atmospheres. That may be possible with small sats, but to do that, it will be actually a challenge on us at the DSN, because instead of communicating sort of on a onesie basis, we talk, actually, yeah, this display is still working. What you see here is, if you can see this display, or if you see it afterward, the display is showing a single DSN antenna communicating with a single antenna, or a single spacecraft. What if you now have many spacecraft around a planet? Now you have to start thinking about, say, the DSN as a cell tower in which it can communicate with multiple spacecraft simultaneously. Also, I showed most of this picture. Of course, we've been to the moon, and then we came back, and we haven't been since. But people are talking about, and the DSN supported that, people are talking about sending humans back into space now, sending them back into deep space to the moon and beyond. I don't know what shape that's going to take, but moving humans and potentially even industry into deep space will require that kind of deep space communication support. And that will be an essential role of the DSN in the future. What that leads to in terms of both scientific discoveries and exploration, well, you might be as good at predicting the future as I am. Okay, this is my final slide. I hope I've made the case that, in fact, over the past 50 years, the DSN has really been an important science tool, and I've given you some hints of where we might be going in the next 50 years. Thank you. I am happy to take questions with the caution that I do not have the full 50-year history of the DSN, and I've been instructed that if you do have a question, please use the microphone so that people can hear.
Yes, I have a question. I was wondering if the DSN was going to add or extend parabola appendages and antennas in the future.
Oh, is it going to add antennas in the future?
Right.
Yes. In fact, it's in the process of doing so. It's somewhat subject to budgetary issues, of course, but the goal is to get additional antennas up to 6 at each one of those 3 sites. And then if you think about communication specifically with human spaceflight, where one can be very concerned about any kind of gaps, there are potential gaps in DSN coverage. It isn't exactly what you'd really like are ground stations spaced at least 100, no more than 120 degrees in longitude, and they're not quite. So there has been some investigation about adding a 4th site on the ground.
I know they have one in Canberra at the current time, and so I was wondering if they were going to add more.
Yes, I don't know the latest in terms of when the completion date is, but there are plans to add more than one to Canberra.
Thank you.
Yep. Yes. And these, I believe, are, well, they came in sort of on the wireless? Yeah, on the Ustream. Considering the DSN was created in the 60s and considering our technological advances since then, are there plans to upgrade the DSN in the near future? The answer is yes, yes in multiple respects, and it's important as well to appreciate the DSN was started in the 60s, but the technology used in it has not been static since the 60s. So these antennas, well, in fact, it was implicit in what I said earlier that the sensitivity of the antennas is such that you have to take the cosmic microwave background into account when you're doing the communications calculations. So these antennas have been refitted with very sensitive receivers. Very typically, in fact, they're so-called cryogenically cooled, which means they're kept at temperatures only, say, a few degrees above absolute 0, which improves their sensitivity. They've been, in one respect or another, upgraded over those past 50 years. Part of the upgrade process is, in fact, adding more apertures so that you get more sensitivity, because part of the limit in sensitivity is just how much metal you can put on the ground, how much you can collect. And then, of course, there's this long-term thought of moving to optical communications, which in some senses is a complete upgrade. If there's not one more from this audience, even with laser technology, how far do you think the DSN will be able to pick up data? Will it be limited to our solar system? Well, I think the best answer to this is the Voyager 1 spacecraft, which is headed out of the solar system. This is the replica, but the thing that's actually headed out of the solar system. It has enough power to last at least until 2020, maybe until 2025. It's moving, if I'm remembering the numbers correctly, about 3 AU a year, which means 1 AU is the Earth-Sun distance. So I won't attempt to do the math in my head real quick off the top of my head because I'll probably get it wrong. But it's moving sort of every year. It moves 3 times the Earth-Sun distance. And it can keep doing that. We can keep receiving the signal for at least the next decade. And after that, then the power on board the spacecraft, the instruments themselves are just going to die. So it won't be able to transmit enough power for us to pick up, unless, of course, we continue to add antennas. The thought of moving beyond our solar system, that's, I think, in principle possible, but remember, these things were launched in 1977. So if you really want to talk about another interstellar faring spacecraft, even if we launch today on a very rapid trajectory, it could still be a couple decades before we have to deal with it. Can I elaborate on the quantum mechanics and the future of communication? I won't go back to the slide. Yeah, the idea behind quantum communication, and it's actually, this is no longer hypothetical, it's been demonstrated. One of the interesting aspects about quantum mechanics is you can generate particles where you know what a characteristic of them is, and let me represent that by using something like this, that the say two particles can have a characteristic like this or like this. You can generate the particles, and the other very important aspect is that in quantum mechanics, you won't know what the state of the particle is until you actually make the measurement. With those two fundamental aspects, what you can imagine doing is creating a particle on board the spacecraft, or creating a stream of particles on board the spacecraft. And then they will propagate so potentially over some large distance. And you will be able to make a measurement of this particle and know exactly, without having measured it, what this particle is. And I fear I'm not explaining it very well, but there is an aspect, the aspect of quantum mechanics is, for instance, if you generate one particle in this direction, the other one has to come out in that direction. So you can actually transmit over very long distances using this quantum mechanical, it's a very weird fundamental aspect of quantum mechanics.
Since you mentioned the beginning of the DSN was Dr. Pickering, and then the people who worked on it actually, Dr. Eberhard Rechten and also Dr. Andrew Viterbi, who were here some years ago talking about it. They did not have at that time all the information you have right now for predicting. How much was their, prediction at that time, back in the 60s, and how much it evolved into what we have right now? I mean, there's some transition at some point. Transition of the knowledge. I mean, when people developed that system at that time, they did not have all the wealth of information we have right now.
No, but there are some pretty, again, there's some pretty fundamental aspects of, for instance, where did that optical? There's some pretty fundamental aspects of just the underlying communications or physics that lead you to things like, okay, there's this kind of spreading of the signal, and that means in order to pick up, if I'm going to send spacecraft to the moon or beyond the moon, I need something that is able to pick up signals that are 100, 1,000, 1 billion times fainter. And you can work out in some fairly simple cases of how much collecting area you need on the ground or how big the antennas need to be. As I indicated in the case with the Voyager, of course, the original dimension of the large antennas was 64 meters. In order to keep up, they had to, the DSN expanded in some sense. I think the real foresight is making sure that you set in place the infrastructure, even if you don't know exactly, they wouldn't have known the Voyager missions in 1963. But they had the foresight to over-design the system in some sense. Build in a way so that it could handle not the missions they were thinking of today, but actually going beyond that. And that's also why if we were going to restart an interstellar mission today, we'd still have the infrastructure to do that. It might take a while to get out there, but we still have that infrastructure today. If there are no other questions, or if people want to take them offline, once, twice.
Yeah. Are there antennas in space? And if so, would they be easier to pick up data than the antennas on the ground?
There are antennas in space. In fact, you see here, among other things, there are the TDRS system, which is used as part of a space network to relay signals within space. The difficulty is that the whole Well, in order to get these very weak signals, in order to pick up these very weak signals, you need very big antennas. Again, you need sort of football-sized field antennas. And launching that kind of thing into space, those are very big antennas. That means they're very massive, and that means it's very expensive. So you can have antennas in space to do, shall we say, local communications, but when you start talking about going out to the solar system, out to Mars, out to Jupiter and beyond, you know, you need things the size of this building, and launching that into space, it isn't practical, and fortuitously, you don't gain much. The atmosphere does not absorb the radio waves very much, so you don't gain very much by actually putting the antennas in space.
You talked a little bit about the smaller satellites, 10 by 10 by 10.
Yeah.
Could you perhaps, since they work in fleets, send one up, then have them form around together to make one large antenna?
I'm missing the picture, but yes, that is, where'd it go? Well, I've lost my, there. Yes, in fact, that is a technique called phasing. There are techniques in which if each one of these is itself small and doesn't have a lot of power, but you can combine the signals in an appropriate manner, you can end up effectively synthesizing a much bigger antenna and transmitting much more power. And that can certainly be thought of from the standpoint of the spacecraft. I think about it as well as not only transmitting, but there's some interesting astronomy that might be able to be done in terms of receiving signals in space. Also, these 34-meter antennas that are being produced, you know, 34 meters is smaller than 70 meters, right? So that would imply that, therefore, the signals, you're not going to be able to detect signals that are as weak unless you combine those 34-meter antennas appropriately, doing this phasing technique, and you can effectively resynthesize a 70-meter antenna. So it can be used both in space and on the ground.
As the number of satellites in orbit radically increase in the foreseeable future, as outer space privatizes, more entities are up there operating, how effective do you think, let's say, the DSN and other deep space communication network community is in terms of lobbying at the International Telecommunication Union to preserve frequencies and to, let's say, plan for the future? Because it's going to be increasingly crowded up there, and is the DSN and the, let's say, the communication community, let's say, adequately represented at the ITU and other fora where these issues are being discussed?
The answer is yes. Let me give a bit of background for those who may not appreciate what the question was asking. The radio, where did I put the picture? The radio part of the spectrum, the radio band, if you will, is widely used. It's used for things, if you turn on your car radio on your drive back, that's a transmission. These things transmit using radio waves. There are all kinds of things that transmit radio waves, and the DSN antennas and our sister radio telescopes are so incredibly sensitive that if that amount of power gets into the telescope or into the antenna, it can actually damage the electronics. JPL takes the lead for NASA in arguing the case at what is called the International Telecommunications Union. This is an international, I can't quite call it a regulatory body, but it's an advisory body that tries to coordinate how the radio spectrum is used internationally. And actually, I do have a picture of the spectrum allocation chart I could pull up here briefly. But the challenge is to coordinate between those of us who are trying to make very sensitive measurements with, for instance, other users who want to transmit and potentially could damage our equipment. We maintain a very strong presence at the ITU trying to argue and keeping at least certain parts of the radio spectrum free to enable, so that we don't blow out our communications equipment and we suddenly have tens of billions of dollars of spacecraft that we can't communicate with. If people will humor me, in fact, I might be able to find quickly, yeah, okay. I might be able to find quickly an example of this. And, of course, doing this on now, this is the United States, and there's a similar one for each nation, and the idea is to keep these all coordinated. I just lost, is this, yeah. To keep these all coordinated, but you can tell how packed the radio spectrum is. All these different, each one of these different little colored bands represents either a different user or a different class of user. And we have to protect, actually I can't read it on here, but there are particular bands that are allocated to deep space communications. They're relatively narrow. They're these one of these very narrow bands. And we have to try to protect those. We have to argue against other users who want to, in some sense, pollute the radio spectrum. So it's an ongoing challenge. Once, twice.
Hi, thank you for your time today. I thought it was a very interesting talk and
Good. Thank you.
history about the DSN. I have a quick question about the recent development with the Chinese space program, and I'm wondering if the DSN was in any way asked or used by their program to manage some of their lunar flight there.
No.
Yeah. Okay.
I was going to go just scroll to the last one to have that back up. Once, twice.
Ashley, could you comment, where are the Chinese tracking stations? Presumably there are 3 of them as well?
I don't remember the details, or at least they are not global as I understand it. They're limited to the Chinese mainland.
So they do have gaps?
Yes,
then.
yes. Whereas the DSN, and again, one of the foresight aspects was that the United States partnered with other nations. And in fact, scientists in both Australia and Spain get a certain fraction of DSN time to use, for instance, for radio astronomy. So we, in a real sense, partner with them. It's not just putting antennas on their territory. We partner with them to conduct both the operations for spacecraft and then other kinds of science.
Thank you.
Shall we call it a wrap? Okay.